In this video, we'll talk about systems of differential equations and what their solutions will look like. We've done a whole bunch of linear algebra. Now we're going to tie it back to systems of equations and eventually see how this linear algebra gets used in the context of systems of differential equations. So, a first-order system, we've dealt with this before. A first-order system is a set of n equations involving n unknown functions and their derivatives. So in general, it's something like the derivative of the first function with respect to time is some function f1 of t and any of the unknown functions that we're looking at. So there's allowed to be interaction. That's the important thing of a system, is these variables allowed to interact with each other. Right? The rate of change of the first one can depend on time, the first one, the second, third, and any of the other ones as well. If they all depend only on themselves, we would have n separate first-order differential equations, but the fact that they can interact makes this a system. So that way, all the way down to dxn dt is some function fn of t, x1, x2, up to xn. And the geometry is written in vector form, where I basically let the vector x be stacking x1, xn as functions of t, as these unknown functions that we're trying to solve for. Then in that case, because derivatives apply to every component, x prime of t is the vector of all these derivatives. And so we can write this system as x prime equals some vector function f of t and the vector x, where really I'm thinking about this vector function f as just stacking up all of these different f's that I had before. And this here is the normal vector form of a system of equations. If it is linear, we can write it with a matrix form. But if it's not linear, we have to leave it like this. There's not much else we can do. It just sits like this. Same idea when we had first order equations. This would be like y prime is f of t y. If it's not linear, you have to leave it like that. But if it is linear, you can move things around to make it look a little bit nicer. Now, what does a solution look like to a system? Well, in vector form, it's a vector valued function x of t that will satisfy the equation once I plug it in. Again, for verifying solutions, all we're doing is taking it, plugging it in, and seeing if it works out. In this case, I have to be a little more careful because it's a system here, and things might interact with each other. So in a sense, this means if I have an equation that has dx1 dt is f1 of t, x1, x2, and x3, so it's a three-component system, I need to check that if I plug x1 here and take the derivative, and then plug x1, x2, and x3 from this same vector x into the right-hand side here, that the equation works out. All the components are going to be involved in all of the process here when you're trying to figure out if this solves the system. And the important thing is, the entire thing has to solve every single one of the equations for it to be a solution of the system. It can't just solve one or two, it must solve all of them in order to be a solution to the system. Again, not all systems are going to be linear, but it will turn out that a lot of the ones we can actually come with for and actually try to solve are ones that are linear. So that's the ones you'll see a lot of the time. But keep in mind, things don't have to be linear for it to be system equations. Again, verifying means we plug in and see if it works. As an example of that, I want to show that this solution here, 2e to the minus 2t plus 4e to the 3t, and e to the 3t minus 2e to the minus 2t solves this given system here. So how do I check? I check by separating the equations and then seeing what happens. So if I look at splitting this up, this means that x1 of t is 2e to the minus 2t plus 4e to the 3t, and x2 of t, the second component, is e to the 3t minus 2e to the minus 2t. Then we can check, what is dx1 dt? Well, dx1 dt is going to be negative 4e to the minus 2t plus a 12e to the 3t. And if I look at the other side, 2x1 plus 4x2 is going to be 2 times 2e to the minus 2t plus 4e to the 3t plus 4 times e to the 3t minus 2e to the minus 2t is going to give me 4 minus 8 e to the minus 2t, so minus 4e to the minus 2t. And then 8 plus 4 is 12 e to the 3t, so this one works. It satisfies both parts of that equation. We have verified for this solution that dx1 dt is in fact 2x1 plus 4x2. Now we do this again for the second part. dx2 dt is going to be 3e to the 3t plus 4e to the minus 2t. And then x1 minus x2 is going to be 2e to the minus 2t plus 4e to the 3t minus e to the 3t minus 2e to the minus 2t. And we can see that we will get exactly 4e to the minus 2t and 3e to the 3t. So this also works, which means it satisfied the second equation. And the last check will be the initial condition, which was given as x of 0 equals 6 minus 1. If I plug in t equals 0 here, I get 2 plus 4 in the top component and 1 minus 2 in the bottom, which again works and solves the initial condition. So therefore, checking both equations with both components and the initial condition says that this here is a solution to this initial value problem. So this is a solution based on the work we have shown here. So that's the idea of a system of ODEs and what a solution might look like, and how it can verify that a given vector function solves the system by plugging in everything all at once. It must satisfy all the components at the same time in order to be a solution of that system of differential equations.